Hello, everyone. Today, I am thrilled to present our work accepted at ICLR, GGBall, Graph Generative Model on Poincaré Ball. Let's start with why we are here. Graph generation is absolutely central to scientific discovery. Whether we are designing new molecules, which are essentially atoms connected by bonds, or modeling social networks, crystal lattices, or protein contacts, the efficiency of AI in exploring these spaces hinges on the quality of our generative models. Currently, almost all existing methods, whether they use diffusion, flow matching, or autoregressive paradigms, share one common trait. They require explicitly modeling edges. They typically use separate channels for nodes and edges, or generate them step by step. But we wanted to step back and ask a different question. Is it truly necessary to explicitly model edges in graph generation? It sounds counterintuitive. After all, a graph is defined by nodes and edges. But let's think about physical reality. In a molecule, whether two carbon atoms bond isn't arbitrary. It depends on their distance and electron configuration in 3D space. In a social network, connectivity depends on the distance in a community hierarchy. Our hypothesis is this: if we place nodes in a good enough space where spatial relations naturally encode bonding, then edges become an emergent property, a function of node positions, rather than a separate target we have to explicitly predict. The real question then becomes, what kind of space is good enough? Traditionally, we default to Euclidean space. However, its volume grows polynomially. As hierarchies get deeper, distances are compressed and distorted. Node positions simply cannot encode enough topology, forcing us to model edges separately. Instead, we propose using hyperbolic space, specifically the Poincaré ball. In this space, volume grows exponentially, naturally matching tree branching complexity. Gromov's theorem proves that trees embed here with low distortion, allowing edges to emerge purely from node geometry. As our chart shows, moving to a hyperbolic model pushes our accuracy into a vastly better region. Our framework is not just a naive replacement of Euclidean operations with hyperbolic ones. It is a complete generative paradigm built natively on the Poincaré ball. We designed this across 3 levels. Level 1 introduces a unified node-only latent representation, compressing the entire graph into node embeddings where connectivity is implicitly encoded. Level 2 implements a 2-phase paradigm featuring a hyperbolic VQ-VAE with a geodesic codebook, followed by Poincaré flow matching. Finally, Level 3 provides the necessary modular components, such as Poincaré fully connected layers, layer norm, and multi-head geodesic attention. Let's walk through the full pipeline. Beginning with an input graph, our first training stage utilizes the HVQ-VAE encoder alongside a geodesic codebook to map discrete structures. This cleverly avoids the KL divergence instability of standard hyperbolic VAEs. For the second training stage, we apply Poincaré flow matching directly on this quantized latent space. During generation, we simply integrate an ODE on the Poincaré ball, apply VQ quantization, and decode the nodes and edges to reconstruct the final graph. Diving into the network details, our Poincaré graph neural network utilizes a unique hyperbolic message passing scheme. This efficiently encodes both edge and node information directly into the node representation. For the generative backbone, we developed a Poincaré diffusion transformer. The core innovation here replaces standard dot product attention with geodesic scoring and uses Möbius gyro midpoints to correctly aggregate values on the manifold. For the hyperbolic autoencoder, input graph features are initially processed by Euclidean MLPs and then projected onto the Poincaré ball via exponential mapping. The encoder heavily leverages hyperbolic GNN layers, while the decoder reconstructs features utilizing tangent space attributes. A critical part of our learning is the codebook quantization, which maps latent features to the nearest hyperbolic centroid and is optimized using both Euclidean and Riemannian optimizers. For the actual generation step, we deploy Poincaré flow matching. Drawing from conditional flow matching, we extend these principles to Riemannian manifolds to ensure that all vector fields remain strictly in the tangent space. Our interpolation path is constructed using exponential and logarithmic maps, perfectly preserving the geometric integrity of the generation trajectory across the manifold. This formulation gives us our highly stable Riemannian continuous flow matching loss. To validate GGBall, we evaluated it on both abstract and molecular datasets. We used community small and ego small to test hierarchical and community-based topology, and QM9 for complex molecular structures. For abstract graphs, we measured degree, clustering, and orbit MMD. For molecular graphs, we assessed validity, uniqueness, novelty, and the combined VUN metric. Our results highlight the undeniable benefits of proper geometric selection. On abstract datasets, our model achieved a 10.4% average error reduction on community small and an impressive 18.2% reduction on ego small when compared against the best baseline. Our geometry ablation is clear. Replacing graph VAE with our HVQ VAE causes an exponential drop in statistical errors, proving hyperbolic space is fundamentally superior for graph representation. Adding our flow model reduces average error by up to 41.9% over Euclidean flow methods. The advantage is even more pronounced in molecular graph generation on QM9. Existing state-of-the-art models like Digress and CatFlow achieve high validity but suffer from abysmal novelty, meaning they simply regurgitate the training set. GGBall achieves the best of both worlds. We attain 91% validity and an outstanding 93.8% novelty, earning a leading VUN score of 85.34. This dual guarantee proves GGBall is actively exploring unseen chemical spaces, a vital capability for real-world drug and material discovery. To visually confirm that our model learned a highly structured chemical manifold, we performed interpolations between molecules in the continuous latent space. Tracking the trajectory from t equals 0.1 to t equals 0.9 reveals very meaningful geometric transitions within the Poincaré ball. The intermediate states remain predominantly valid molecules and exhibit smooth, logical topological morphing, like naturally transitioning from rings to open chains. This brings me to a broader perspective for the field. We need to balance where we generate against how we generate. Much of our community's effort goes into iterating paradigms, from VAE to autoregressive to diffusion to flow matching, which are primarily algorithmic improvements confined to a fixed Euclidean space. We argue that exploring geometry introduces powerful spatial inductive biases. Geometry is a crucial degree of freedom. Letting the latent space naturally accommodate the data's topology significantly reduces the learning burden. Mixed curvature spaces are the next frontier. To conclude, I will leave you with 3 key takeaways. First, spatial bias can indeed replace explicit edge modeling, helping to unlock graph scaling bottlenecks. Second, with GGBall, we provide a fully validated, modular, and out-of-the-box pure hyperbolic generative pipeline for the community. And third, we hope to inspire a paradigm shift. Optimizing geometric bias is just as critical as iterating on generative architectures. Looking ahead, we plan to apply these concepts to mixed space modeling, hardware topologies, and biological networks. Our code and paper are available online. Thank you very much for your time and attention.